Hey, George, you're a scientist.
I'm a chemist, yes.
Right, you're a scientist. So, I'm I'm going to bring to you a question that I'm going to say comes from a listener, even though he probably wouldn't call himself a listener. I was watching a CGP Grey video, and he is also a scientist. I think his background is actually in physics. And he just sort of flippantly mentions in some other conversation about something else, ice-3 and ice-9 as, I'm not even sure what the right term is, like orientations of frozen water, I think, that don't align themselves the way like normal ice does, right? So like normal ice forms like a crystalline lattice structure or something, and ice-3 and ice-9 do something else. But this is the kind of science that I firmly remember hearing about, like at the end of high school and in some early college classes, but then never having to go any deeper on, is when it's like, oh, here's a familiar element. And it's like, oh, I know that familiar element. And here it is with some Greek letters and numbers tacked onto the end. And I'm like, I don't know what that changes. Is oxygen alpha 15 the kind that makes me into the Hulk, or the kind that gives me cancer? Right? Like, I don't know, because I don't know what any of those modifiers mean, right? Usually it just means cancer.
Yes.
Or it means that thing can only exist like under super extreme conditions, but I don't like what even is it? What is ice-3 and ice-9? And are they even the same thing, or do they just sound similar?
Well, darn it, Lions, I am a chemist, not a physicist, like this other person is. But with my very limited knowledge and very limited expertise, I will attempt to opine to this. So when you first said, what's ice-3 and ice-9, I was like, ice is ice, and I just... I was like, I'm not going to tolerate this. And then I was like, no, let me look into it. And I did. And I learned some stuff. So, but first let's take a step back. What are the phases of matter?
Well, you have a gas, a liquid, a solid. And then if you're cool, you also count plasma.
Yeah. Cause that was the one where you learned about it in high school. And then you went back to all the people in middle school, and you're like, how many phases are there? And they're like, solid, liquid, and gas. And you're like, no, nerd, there's plasma too. And it's like, well, what is plasma? You're like, I don't really know, but I know it's one of them, and you didn't, so I'm better. Yes, absolutely. And yeah, plasma is one of those ones where it's like, it doesn't exist. Like, you don't normally point to it and say, hey, look, plasma. And also too, it's like, we need a separate thing because things are getting weird. So
the balls with like the purple lines that you could buy in like a Spencer Gifts and like put on your shelf. Is that actually, I remember people saying that was plasma, but I don't know if it actually is.
I don't think that's plasma.
I don't think it is.
I think if I remember correctly, and this is off the top of my head, the reason why plasma is its own thing is because it has the properties of like both a liquid and a gas. Because it's because of where it's at, and we'll get to that in a second. It's like, well, it doesn't really behave like either, so we kind of need to give it its own thing, but it doesn't occur naturally. So normally you're like, look, solid, liquid, gas, that'll get you 99% of the way there. And if you're going to go do science, you might need to know about this fourth one. So what separates these different phases, right? So if you wanted to take something into these different phases, what are the things that you could do to it to push it into one phase or another?
Well, I think if I'm thinking about water specifically, which may or may not be representative generally, but
let's keep with water.
Yeah. I would think of water that is in a solid state has less energy in the system and is more dense. And then as you add energy into the system, it also loses, the density goes down, right? So like a gas you would have way less gas in the same volume than you would have of a liquid than you would have of a solid.
Interesting.
And I'm basing that off of like, you would heat ice to turn it into a liquid and then into a gas, and that the water vapor would take up more space than like the individual ice cube.
Yep. So interesting.
Oh, wait, no, wait. Water famously expands when it freezes.
There we go. Yep. No, wait, shut up. I was like, interesting that you decided to keep this in the domain of water because that you were going to be right 98% of the time, except for the one example that you chose. Yeah. So to your point, right? Water is less dense when it's solid. So there's a reason why we define these kind of states the way that we do is because if we said like, oh, well, it's a solid, it's a liquid, it's a gas, each one kind of has its own properties, but they aren't uniform or ubiquitous. But like if you think about, because you've seen like the graphs of like, oh, well, water is a liquid at this thing and like a gas over here. Do you remember those? Do you remember what were on the axes of that graph? You already named one, which is heat.
Yeah, so temperature. And well, I speculated volume, but it's would it be pressure?
It is pressure. Well done. Yes. Got it in 1.5.
I'll take it, dude.
But yeah, so that's the thing is that it is basically if you look at like a solid, right, is that all of the atoms tend to be like locked into place, right? They're really close to each other and they're just kind of vibrating a little bit, right? And so as you pour heat into that system, pour kinetic energy into that, they get a little rowdier. And they get a little rowdier. And then all of a sudden, they're like kind of like mosh pitting it up. And they're all kind of like moving around each other. But they're still, playing it pretty close, right? And you keep pouring more energy. They're getting rowdier and even rowdier until all of a sudden they're just like, aha video, like bouncing off of each other, right?
It's like the end of the second Mary Poppins where they're all like flying into the sky.
Exactly, right? And so thus you have the solid, liquid, and gas. But like let's say that you've got a whole bunch of people, they're all energetic, right? They're all throwing back Four Loko or whatever nightmare fuel people are pouring into their bodies these days, right? And so they're about to start flying apart, right? And like really getting going. And then you make the room smaller, right? Well, now they can't fly apart as much, right? So if you keep pushing down the room, even though they have the same amount of kinetic energy, right? They're being forced to be closer together, right? So thus, the greater the pressure, the more likely they are going to be solid, and the lower the temperature, the more likely it is to be solid. The more you reduce either of those two things, the more likely they are to move into a liquid and then into a gas. So I say all of that to say, what is, so when we think about water, right, what is the shape of water, if you kind of had to throw a shape at it?
Is that a romantic comedy movie, The Shape of Water, or like a book of poetry? It's something.
Oh no, it's not a rom-com. That was a weird movie where they have sex with the fish.
What?
No, yes, it was a famous thing. Right? No, it's Guillermo del Toro, and I'm not crazy.
I feel like you're gonna need a minute to like panic Google
this.
I'm
looking it up right now.
Yeah,
I'm not crazy.
Yeah.
It's a 2017 fantasy romance movie with Sally Hawkins, Doug Jones. Yeah, no, like, and that's the whole thing is that she like falls in love with like a mermaid person. And yeah, but like the whole thing is that apparently, I've never seen it, but apparently there's like a very romantic and I believe like basically like a sex scene where it's like, yeah, and that was like the thing that everybody was talking about. I'm not crazy.
You're not crazy. I was happier when I thought it was just a rom-com or a book of poems.
Nope. It's the other thing.
Although Del Toro tends to make pretty good stuff, so maybe it's tasteful interspecies sex scene. I don't know.
It was supposed to be like from this is what we're going to talk about now.
Yep.
Is from what I remember, because again I did not see it, is that is people talking about, like, everybody who was legitimately critiquing it said it was a good movie. Anybody who was doing like the 1 second like flyby of it, it was like, oh, isn't that because like somebody'd be like, I went to go see The Shape of Water and it was really like evocative and very meaningful, and then somebody's like, oh, you mean the fish sex movie? And it's like, so
which I mean is on par for the discourse of most things on the internet. Yeah. So I guess that's not really his fault as the auteur filmmaker. What on earth was your original question?
No idea. Oh, what's the shape of water?
What is the shape?
Actually,
right. It was literally.
Yeah, right. Yeah. Oh man, I really kind of this is on me, guys. Yeah. That's my bad. Legit. That's how far into the science I was with it. I did not even think. I was like, yeah, what shape is it? Anyways,
yeah.
Yes.
So water is a low viscosity liquid, so its shape is the shape of its container.
It is that. Sorry, allow me to be more specific. The shape of the water molecule.
Oh, I mean H2O, so you have hydrogens hanging off of an oxygen.
Yep. But do you know what shape would you call it? Like if you so basically
Oh, I get like a V, I guess.
Yeah, like a V. Yep. A V or basically like a triangle, right? You know? So yeah, triangle, a V, but basically it's got like kind of a point, which is where the oxygen is, and the two hydrogens come off. It's famously not a line, right? It's not HOH all in a line, right? Is that it's got that bend to it. And the reason why
wild to me that matters. Right? Like it is so hard to imagine something that small having like a meaningful shape and orientation, but they super do.
Yeah, no, it matters exhaustingly to organic chemists, man. Because because exactly like what angles they're bent at and like how they're bent. And then if you try to like do different bonds, it'll force it into being like an unnatural bend. And so therefore it has like more potential energy and more likely to fly apart. Yeah, it's a nightmare. The reason why this is actually shaped like a triangle is because the oxygen has two unpaired sets of electrons and they hang out on the top of like the oxygen typically, right? And the oxygen kind of hoards, as we've mentioned before, it has a dipole moment and hoards all of the electrons, right? And the positively charged hydrogens kind of like relinquish them a little bit. So the oxygen is slightly negatively charged and the hydrogens are slightly positively charged. And thus we have now made a puzzle for children, right? Where it says, hey, arrange these so that way positives touch positives and negatives, or positives touch negatives and negatives touch positives, right? And that's basically what ice is, right? But the cool thing is that there is more than one way to do that, right? You know, so you can just arrange them all in like their normal, tetrahedral shape, right? Or excuse me, their normal hexagonal shape, right? And they will, they will arrange themselves appropriately, right? But it's kind of like how. Well, let me take a step back and say, so for example, if you like a diamond is made out of carbon, right? As is graphite, as is a Buckminster fullerene, right? So all of these things are made out of carbon. That's the difference between ice-3 and ice-9 and ice, right? Is that it's just how we've arranged and oriented all of these different types of ice. So that's we've now made the universe, right? So we can now talk about the specific subject matter. So when I said ice is ice, and then I went to look it up, I was like, oh no, because it sounds like ice-3, right? It's like, for example, you've got uranium-235, right? That doesn't mean that there's a uranium-1 and a uranium-2 and a uranium-3, right? Uranium-235 says like that's the atomic mass of the nucleus, and then there are other radioisotopes that kind of fall off of that, right? So that's not true with the ice system. In fact, ice H or ice 1 is ice, right? Like that's ice 1H, ice 1 sub H is ice, right? And then so ice 3 is a different type of ice, but then that means that there's an ice 2, right? And so ice 9 would mean that there's an ice 4, 5, 6, and 7, and 8. So it goes all the way to ice 19.
Come on, dude. Like, it's not.
No, you did this.
It's not that complicated. Like, water is not that complicated of a molecule. And there's 19 that we know of combinations that you can, like, at different temperatures and pressures, get ice to happen.
Yep. Yes, exactly. Depending on how the ice is formed, like under what conditions the ice was formed, under what temperature and pressure the ice was formed, it will form a different crystal lattice structure with different. And the thing that matters is it has different physical properties. So like for example, ice has a density of so water has a density of 1 gram per cubic centimeter, right? Which makes it super easy, right? Ice has a density of 0.917 grams per cubic centimeter because it's slightly less dense than water, right? However, ice 3 has a density of 1.16 grams per cubic centimeter. So it's actually more dense than water, right? Which is really great because that whole thing that you like jumped all over, I was going to give you the opportunity to say it wrong, and I was going to correct you, and then you could correct me now, because ice isn't always less dense than water. Sometimes it's more dense. So if you ever make that mistake again, wait for someone to correct you, and then be like, well, no, sorry, I was talking about ice-3.
Yeah,
you know,
obviously that's what I was doing.
So this giant table that I was looking at, so it looks like in around the early 1900s is when we suddenly had this like explosion of discovery of ice-2, ice-3, ice-4, and ice-5, right? We were like, oh, hey.
There is a very like jokingly named chapter in a history of science textbook somewhere about this, right? Like, like those were the cold years when we discovered all the different kinds of ice.
I really do feel that if you looked at like, so like I said, 2, 3, 4, and 5 all discovered in like the early 1900s. I really feel that if it's like, you looked in a history book, it's like, you know, John Smith went to explore the Arctic for the first time in 1905. And you're like, oh, well, no, that lines up, right? And they're like, as a scientist with his ice coring machine, and it's like, yeah, no. So we got all of those on the first pass. The funny thing, one of the other funny side notes about this table that I looked up is for ice 1, for year of discovery, it says always known. And I like that. Like, because it's funny. Ice. Yeah, right? It's like, no,
we do not know when humans discovered ice.
It was probably like the first thing we could genetically call a human, and then they said, hey, look, there's ice. And then, ta-da.
Yeah, got it. Update the Wikipedia article.
Yeah, and so some other like fun things is like a lot of these require gigapascals of like pressure in order to get them to form. A lot of them specifically calls out, so for example, ice-6 is formed at 1.1 gigapascals from liquid water. Ice-7 is formed at 2.2 gigapascals specifically from ice-6. So like all of these are like Minecraft recipes for like how to make these things, where it's like, okay, I need 1 unit of ice-6 and then this much of this and this much of this, and then I can form this, cool little thing. And this also kind of shows how deep this rabbit hole goes, because the some of the things that it says like in like special notes on this table, I'm like, man, I know I'm just a chemist, but I feel like anybody who's not an ice expert wouldn't know what half of this stuff is, right? So, for example, one of them for ice-7 is the hydrogen atom's positions are disordered, exhibits Debye relaxation. The hydrogen bombs form 2 interpenetrating lattices, tetragonal form contested, known as ice-7 sub T. And I'm like, what? Because I don't know what Debye relaxation is, and I'm like, I could spend the rest of my life on this page just doing deep dives onto each one of these like sub little things. Also too, because, and this is, I truly believe like the golden age, like a golden age of science, right? Because the more contributors that we have in a society, the more people that we can have that are looking into this sort of stuff and not like making food, right? So it's good. A rising tide lifts all ships, and apparently 19 different types of ice. So I say all that though is to say like the amount of clear, snarky arguments that are happening in this table scientifically, I also found great joy in. For example, ice-10 was discovered in 2022, but it was contested. And I don't really know what that means, but someone's getting argumentative about it. So
somebody wrote an academic paper or maybe a dissertation, and then somebody else was like, no, your measurement methods were wrong. Your whole experiment was flawed. No one could conceive of a double-digit number of ice.
Yes, exactly. Or, somebody was like, oh, well, I discovered it in 2022. It's like, oh, but I discovered it in 1996. And it's like, yeah, but your results were not reproducible, but mine were, because you did it at 165 Kelvin, but I did it at less than 140 Kelvin, which means that my ice-10 is more. It's like, oh my God. And one other note I'll make about this particular table is there is approximately 50 different citations for this table. And I like that a lot, because it means that there's just so many scientific articles to link to about this particular stuff. And, that's a good thing.
I think it is. What I want to know is and you may not have a concrete answer to this, but this feels from the outside like, oh, this is pure research. This is just someone saying, well, what if we take ice-19, the iciest ice we know of so far, and we fiddle with the knobs a little more, and we change the temperature and we change the pressure? Can we get a new ice-20 that is not like any of the previous 19 ices, right? And that's cool. I mean, I'm with you on the contributor thing, right? I am totally fine with somebody doing pure research, but what is often hard with something that is scientifically or engineeringly complicated beyond one's reckoning is imagining a practical application of any kind, right? Like maybe it's this would be a mega coolant in rocket engines or something. I don't know. But like, are there any known applications of any ice besides ice 1? Because I know what ice 1 is for. Like that one I have a pretty solid understanding of.
It's for cooling your drinks.
Yes, and nothing else. That is its one and only purpose. Oh, also sinking boats.
Yes. Well, no, it's unintended purpose.
Oh,
you know?
Okay.
So that's what happens when you don't use ice to cool your drinks. If you use it for other stuff, people die.
I'm not an ice scientist. But are in your research of this, did you come across any are there any like applications of this knowledge, or is this knowledge for knowledge's sake? I'm not going to call it trivia, but like knowledge for knowledge's sake.
So to your point, right, is that there's a lot of times when people are like, well, why are we researching this? What's the practical application? And it's like, we may not know yet, but at some point somebody could say, I need a substance that can do a non-toxic substance that can do X, Y, and Z. And it's just like, well, no known substance exists, except, well, you know what? We did just discover ice-19, and it checks all of those boxes, right? That being said, there are practical applications, most of which are beyond my understanding.
Okay, like, I'll take that.
Well, because I got a couple of them here, and they're friggin' fantastical. Because like to me, it's just kind of like if you know, as the premise says, like I'm the scientist, right? Is that you know it's like you're like, oh yeah, like look, George is like 5 steps on the ladder above me, and he's gazing out. And oh, actually, I take that back. You know what this is? This is a story that we will share for our audience. Is for my bachelor party, we decided to go hiking, and we decided to go hiking up a mountain, right? And as we were hiking up a mountain, we crested one of the ridges, and I just happened to be the first one up. And right as we crested that ridge, I suddenly looked onto a sea of fallen trees and huge craggy precipices and just a nightmare of a hike. And I said, guys, things have just gotten real. And I remember you yelling up, I thought they were already real. And I said, no, they have become real just recently. Like, that's what we're dealing with, where it's like, I consider myself to be a scientist, and I don't know what half of this stuff is, man. So amorphous ice is used in some scientific experiments, especially cryo-electron microscopy of biomolecules. The individual molecules can be preserved for imaging in a state close to what they are in liquid water. Neat. I don't know what any of that is.
It sounded scientific, though, right?
It does, right? And
those are some good science words.
Ice-17 can repeatedly absorb and release hydrogen molecules without degrading structure. The total amount of hydrogen that ice-17 can absorb depends on the amount of pressure applied, but hydrogen molecules can be absorbed by ice-17 even at pressures as low as a few millibars. And that's one of the things where I'm like, that sounds important. That sounds like a thing that if you need it, you need it, and you know exactly what you're using it for.
Yeah.
I don't know what that is.
To a layperson, what that sounds like you just described is someone is doing something where what they need is a bottleneck for individual atoms. Right, and they're like, oh, I need to pass individual atoms through this space, and the only way to do that is by shooting them at ice-9 or whichever one,
ice-17,
ice-17, and then having it like be emitted safely out the other side.
The last one I'll read is aside from storing hydrogen via compression or liquefaction, it can also be stored within a solid substance, either via reversible chemical processes, chemosorption, or having the hydrogen molecules attached to the substance via the van der Waals force. Physisorption. The latter process can occur within ice-17. In physisorption, there is no chemical reaction, and the chemical bond between the two atoms within the hydrogen molecule remains intact. Because of this, the number of adsorption, not absorption, adsorption, desorption cycles ice-17 can withstand is, quote, theoretically infinite, end quote. So I like that for a couple of reasons. One is because there's a whole bunch of wild stuff in there. But the fact that this article quotes theoretically infinite and then immediately has a citation behind it means that the paper that they're quoting, they're quoting that directly. And I can just picture that in a scientific paper where it's like, this is theoretically infinite. And I'm like, I don't know, man, that makes me happy. This all makes me happy.
Well, I'm glad that I was able to come up with something that you went through the full scientific gamut on, right? Like your human reaction was, that's stupid, that's not a question. But then your scientific reaction was, but is it a question? Right? And then you picked it apart, and you now have had an opportunity to say a bunch of words that I assume are real science words, but that I assume most people listening cannot fact check you on.
Well, and that's the thing is that, so somebody once said recently, and I really appreciated it, which is that when you say the phrase, that sounds right, what you're saying is that agrees with my existing biases,
mm-hmm.
right? And so, I mean, obviously we're humans and we have to rely on some of our like biases because we can't, run everything to the ground. But I was happy when you're like, hey, what's ice-3 and ice-9? I'm like, dude, ice is ice. Ice-3 and ice-9, that disagrees with my existing biases. But then went into it, I'm like, oh, but I was wrong. I was way wrong. And I learned something. And now hopefully everybody's learned something.
Yeah, this does remind me of another ice I wanted to ask you about.